David Weld received his PhD from Sheffield University's in Information Studies in 1994, and he's the director of the Cheminformatics program at Indiana University, Bloomington, and we're fortunate to have him give a try with this new Big Blue Button program that we're using with Skype on top of it, and hopefully everything will work fine. So David, I'm going to turn this over to you.
Great. Well, thanks very much, Bob. Okay, if everybody can hear me, wave your hands. Okay, wonderful. I like to do that at the start, then it gives you permission to fall asleep later on in my talk. So I should say just a little bit about my background. I was originally, a long time ago in the 80s, a computer scientist, and then I got involved with what was then called computer-aided drug discovery in the early 90s, and did a PhD in it in the UK. And that was really kind of set off a career for me in this field. I did a postdoc, and then I worked for several years in the pharmaceutical industry in Ann Arbor in Michigan. I worked at Parke-Davis, and then moved to Bloomington, Indiana in 2005 to kind of move back to academia. So my kind of field is what's now called cheminformatics, but really back when I started, it didn't really have a name. It was just using computers in interesting ways in chemistry and drug discovery. So we kind of see this field of cheminformatics build quite substantially over the last 10 years or so for a variety of reasons, from the pervasive use of computers through to the fact that we have much more public data now available relating to chemistry and biology than we used to. So it's really, from my perspective, quite an exciting time in terms of what we're able to do with computers in chemistry and in the fields that chemistry impacts, like drug discovery. So do feel free to kind of, I guess we'll keep most of the questions for the end, because we're going to have to do the microphone thing, but maybe just kind of, if something really interests you, jot it down, and we'll definitely try and make some time to cover questions at the end. You'll have to excuse me as well, I'm just getting over a cold. It's not quite winter weather here, but it's certainly cold enough to have some bugs going around. So the things I'd like you to be able to get out of today are as follows. We're going to kind of take a fast kind of 200-mile-an-hour zoom through cheminformatics today, but so most of it is just really going to kind of whiz by you, and its purpose is just to kind of leave a bit of an imprint and a seed, so it might be something you come back to later. But the things I'd like you to be able to take away from today is, first, have sort of basic understanding of how we handle chemistry on computers, how we go about representing 2D and 3D chemical structures on computer. We have something called a SMILE string, which is a nice computer-friendly way of doing that. Second, have some understanding of the part that things like data mining, molecular docking, virtual screening have in modern drug design. Discovery of new drugs is a massive application area of both chemistry and of cheminformatics. And again, it's a really kind of key crux time. If you follow any of the kind of news stories about the pharmaceutical industry, is kind of trying to reinvent itself and is trying to find new ways to discover new drugs, and informatics is really at the center of that. And finally, just have a few slides on what I think are some of the current trends and future direction of cheminformatics. I can talk endlessly about my research, but I'm not going to do that today, but I will give you a few pointers as to things I think might be interesting. So to talk about how we represent chemical information, chemical structures on computer, we really have to go back to Chemistry 101. Now, you might say, no, I don't want to go back to Chemistry 101. I'm a graduate, or I'm a postdoc or professor or whatever. Well, this isn't the Chemistry 101 that's about or distilling alcohol. This is the Chemistry 101 about what is a chemical. What do we really mean by a chemical? It turns out this question is more complicated than we might like to think. If you think of chemistry being placed somewhere between physics and biology in terms of complexity, physics tends to deal with what are in the main quite simple conceptual things, so atoms or atomic things, and quarks and points in space and such like. And so representing them tends to be quite straightforward. On the other hand, biology is so complex that often we don't even try and we can't represent a liver on a computer, so we don't even really try and represent it. We just give it a name and talk about it. But chemistry is kind of in the middle, where it's kind of systematic. It's about building blocks, atoms, which form together into molecules, and what those molecules do in reactions which make the molecules. So it's systematic enough that we can think about a quite detailed representation on a computer, but it's not straightforward enough that it just becomes a trivial, storing a coordinate in space, or storing some data points about one fundamental particle. So chemistry is kind of historically developed to kind of take into account that complexity, and with that we've developed ways of representing chemicals just in textbooks, on paper, in journal articles, wherever, that reflect that kind of span of trying to represent the details about chemicals through to representing the kind of just overall properties, or just a name for chemicals. So we have these three particular ways that have developed for representing chemicals. Firstly, the trivial name, baking soda, aspirin, citric acid, which really tell us nothing or very little about what is in a molecule, what's in a chemical. There's some clues, citric acid is an acid, but really the word aspirin doesn't convey anything about what atoms there are in aspirin, how they're connected together by bonds, what it does. It's just a name. So a little bit more information is contained in the chemical formula. Specifically, the chemical formula contains the atoms which are present in a molecule, but not how they're connected together. So C6H12O6 has 6 carbons, 6 oxygens, 12 hydrogens. But we don't know how they're connected together. There could be many different molecules with that same formula. Finally, the systematic name goes one step further in detail and actually represents not just what's there in atoms, but how they are connected. So 1,2-dibrommer-3-chloropropene fairly unambiguously represents what's going on, not just with the atoms, but how they're bonded together. However, the systematic names get very, very verbose, so they tend to have fairly limited use. We also have these things, depending on who you are and what your background is, it can be many different things. If you're a web designer, this is an image. If you're a chemist, it's a 2D chemical structure. It conveys massive amounts of information. If you're a computer scientist, it might be some kind of graph or network or something. But this is a 2D structure diagram, which is really the lingua franca of chemistry. And it's how most chemical information is conveyed in some way, in various ways, in a journal article representing a reaction, or in a database representing a drug or whatever. So as chemists, we're so used to this kind of representation, we don't really think about it. So this is actually tyrosine is a trivial name, and then this is the systematic name for tyrosine, this amino acid. But this little picture here isn't actually very friendly to a computer. Now, all a computer sees when it sees this thing is a picture, an image, a JPEG file, a GIF file, whatever. It can resolve nothing about the fact that this is a chemical compound that contains carbons and oxygens and carboxyl groups and benzene rings and all kinds of things. It's just a picture. So we've got this collection of human representations, but there's not really obvious ways of saying how do we transfer that to something the computer can understand. And I teach a course on information representation to undergraduate students, and I keep trying to press into them that computers can be really, really clever, but they're also really dumb. And most of the time, it's us that have to make the adjustment. We have to make this adjustment to shift our way of thinking to the computer's way of thinking. And it's the same with chemistry. We've got to make these adjustments. So a lot of what we'll be talking about today is kind of what those adjustments are that we have to make, and then what we can do once we make those adjustments. So cheminformatics, or the roots of cheminformatics, if not the name, go right back to the 1960s, and actually a little bit earlier in some regards, when some very early pioneering chemists started to think about these questions, particularly how do we communicate structural information, these chemical structure diagrams, between humans and computers. And once we get them on the computer, what do we do with them then? How do we best represent them internally? So we'll be looking at some of these. There's a kind of key, really good development that happened way back then because of a problem. There was a problem that most of the computers around couldn't do graphics. You couldn't draw chemical structure. You could just type in text. So the only way to represent the chemical structure diagram was some way to communicate. It was some way to convert it to text. So we've got these things called linear notations or line notations developed. The earliest was Wisswasser line notation, which is a way of representing a chemical structure as text. But this has been fantastic ever since, because once we cracked that, we can then do things like storing a chemical structure in an Excel spreadsheet cell or in a database field, or just in a normal text file without having to worry about drawings and images and all this kind of thing. So it turned out to be a really good development. The one that we use now is called Smiles. That's the most up-to-date one. There's also one called Inchi. The Smiles and Inchis are the two you'll come across now. But Wisswasser line notation was really ahead of its time. So linear notations or line notations represent the atoms, bonds, and connectivity model of a molecule in a linear text string, kind of what you're representing in a systematic name, but in a way which is much more friendly for computers. Here's an example of a Smiles. This is, I think this is Tylenol. Hopefully you won't need any after my lecture. No, actually, is this Tylenol? No, this is... That's organism. Well, I think that's the amino acid, isn't it? But anyway, this is chemical structure, and then we have one possible Smiles for this chemical structure. I say one possible because any one structure can have many Smiles depending on how you want to go about deriving the Smiles. The way this works is that you have letters in the Smile string which represent different atoms. So O's mean oxygen, C means carbons, equal signs mean double bonds, N's means nitrogen, and we use parentheses to represent branching. So very briefly, if we go through this molecule, I have an O means this oxygen here. We don't actually represent the hydrogen as it can be implicitly derived. Then we have, so this O here maps to this oxygen here. Now we move along the chain, then we've got a carbon here, but then we have a branch off, and we use parentheses for branch. So we have this carbonyl group here that's branched off here in the Smiles. Then we go back on track, and we have a carbon with a nitrogen branched off, carbon, and then we have a ring system. We'll get to how to represent those, and then we have a hydroxy and oxygen hanging off, which is here. Okay, so it's a really neat way to just take a chemical structure diagram and collapse it down to a piece of text that a computer can handle. So some of the basics, atoms are represented by their chemical symbol. For the common organic ones, we don't need to do anything. For other ones, we have to put them in square brackets. But for the regular ones, we can just represent them as the chemical symbol. So propane here would simply be represented by CCC in Smiles. So there's an implicit single bond. Anytime we have two letters next to each other, there's an implicit single bond. One propanol here, CCCO. Notice that this could be CCCO or OCCC, depending on where we start. Okay, so we actually, it's a bit more advanced topic, we have something called the canonical Smiles, which is a unique way of numbering the atoms in the molecule, so we always generate the same Smiles each time, which can sometimes be useful. Here we've got a double bond popping up, propene, and we just use an equal sign for that, so C equals CC or CC equals C. To propanol, we have a bit of branching. We branch this oxygen off here, so we go carbon, carbon, oxygen branched, and then carbon. No need to represent the hydrogens because they can be derived from the valency. Now rings, ring systems. So the way we handle rings is through this use of digits here. Now, what a digit does is it allows you to specify an extra bond which doesn't have to obey that adjacency thing. So normally we have these implicit bonds between the carbons, or we can explicitly say a double bond or whatever. But if we use a digit, any digit between 1 and 9, then any time this in the SMILE string it finds the same digit twice, it'll put an extra bond in between them. So by far the most common use of this is to make ring systems where we can just add an extra bond between the last carbon and the first here. So here we've made cyclohexane, C1, CC, CC, C1. We can make that aromatic simply by making the letters lowercase instead of uppercase. This is an aromatic ring, a benzene. And this can bring up a whole bunch of issues to do with aromaticity and tautomerism and delocalization of electrons as to what is aromatic, which we won't get into here. But suffice to say, there's some subtleties involved in aromaticity. But we can use lowercase letters here for aromatic compounds. Then we can do branching off that. So we can have chlorobenzene here. We'll put a branch off the ring here for the substituted chlorine here. And here we've got this is acetaminophen. I guess it was before. Yeah, I'm losing it. So here we have acetaminophen. We have what we're going to do here is we're going to start. Let's see. I think we start on this one probably. So we start here, and there we go. C. So we're going to make this. It's going to be ring system aromatic carbon. Another aromatic carbon here. Then we have the oxygen branched off the ring, and we have 1, 2, 3 aromatic carbons. Then we're going to have another branch for this whole thing here. We have a nitrogen, a carbon, and then a nested branch, another branch off the branch for the double bonded oxygen of the carboxyl. Close it again, end with the carbon, close it again. We'll go back to the carbon, then close the ring system. Okay. We can actually do multiple ring systems and all kinds of stuff with this. It's actually been shown that your SMILEs can represent any structure. Here's another one, Nindole, with a multiple ring system. This can get a bit tricky with aromaticity. So a few other things here. We can have charge, put charges on. We can use asterisks for unknown atoms. We can actually put stereochemistry in with something called isomeric SMILEs. We can specify bonds coming into the page or out of the page. And as I said, we can make canonical SMILEs where the SMILEs comes out the same every time. And if you want to know more about this, you can probably just do a Google search for daylight and SMILEs. So there's a guy called Dave Weininger invented SMILEs. He made a company around it. This web address will take you to the SMILEs homepage with a lot more information. I should say, so for a lot of years, SMILEs has been a kind of de facto standard linear representation for structures. A few years ago, IUPAC came up with inches. Inches are meant to address some of these issues I talked about with stereochemistry and tautomerism and such like, and they're kind of gaining usage. I think Tony will mention them next week in a little bit more detail. There's a little bit of momentum going for inches. So as well as SMILEs, a similar kind of idea, but a different format, and kind of a little more web friendly as well. So that solves the problem of how to get the chemical structure onto the computer. Then you have the question, what do you do with it once it's on the computer? Well, here we have some, computers like dealing with ones and zeros and tables of ones and zeros and things. So what we really do is we find the most computer think friendly way of representing what's in that structure. And what's in that structure? A bunch of atoms and then a bunch of connections between atoms. So we do that in two ways. We have a thing called an atom lookup table, which is simply a table where we're given a numbering to each of the atoms. So we have various ways of uniquely numbering atoms. And then we can apply a label, which could be as simple as just the type of the atom that it is, or can be more involved with different hybridization states and charges and such like. And then we just can cross-reference any atom number to those other bits of information. As for some reason, we've got this little rectangle popped up here. So if you can just ignore the rectangle here. Actually, is that a? I wonder if that's a. Oh, there it goes. It's gone. Lovely. So the connection table is then to say what bonds there are and what for each bond, which two atoms it bonds together. Now, this is a very computer-friendly format called an adjacency matrix. In the adjacency matrix, we have a row and a column for each of the atoms, and then at the intersection of the row and the column, we say whether or not those two atoms are bonded or not. So here we have, for instance, atom 8 and atom 3 up here have a single bond between them. So the intersection of 8 and 3, we have a 1. Now, a true adjacency matrix only has 1s and 0s. Usually with cheminformatics, we also use 2s to represent a double bond, 3s for a triple bond, and sometimes 4 for a aromatic bond. But the principle is the same. This is a matrix, a mathematical matrix. And mathematical matrices are really useful on computers. What mathematical matrices and adjacency matrices also do is open up this big bag of extra techniques called graph theory. Now, graph theory is a branch of mathematics which studies graphs. And a graph, mathematically, is any instance where we have a set of things in connection between things. So classic examples are the London Underground map, where the things or the nodes are the stations, and the connections or the edges of the train lines between stations. Or we have these classic problems like the travelling salesman problem. Here the nodes are cities and the edges are either distances or roads between cities. We have these problems like calculating the shortest path for a salesman to take in, n different cities in the US. So it's a classic computer science mathematics area, and there's lots of algorithms being developed for that particular area. Oops, sorry, my cell phone I forgot to turn off. And so by using that matrix representation of the chemical structure, we open up this bag of available techniques to use on our chemical structure. How do we do it? Well, what we can do is we can think of the 2D structure diagram as a graph. The atoms become the nodes and the bonds become the edges. We have to think about a few things. Normally we don't include terminal hydrogens because they can be implicitly derived. Sorry, that's my office phone. But of course, someone decides to ring me on all my phones at once. We tend to we sometimes do things like reduced graphs where we kind of summarize things in one node. But generally, you can think of the atoms as nodes and the bonds as being edges. So this opens up this big bag of algorithms and things which enable the computer to do some things that we normally do with our eyes, but the computer has to do using graph theory. So, as humans, we're really good at looking at pictures of things and finding connections and things in the picture. So we can look at a 2D structure diagram and see all the connections and understand them. The computer really isn't very good at that. But you can look at a matrix and apply some graph theory techniques and then achieve the same ends. One example is subgraph isomorphism. A subgraph isomorphism algorithm is a graph theory algorithm for finding one graph within another. Does this graph contain this other graph? Well, this is really useful in cheminformatics because the subgraph can be a substructure and the graph is the molecule. So if we want to ask a question like, does this molecule contain a benzene ring? Or does it contain an imidazole? Does it contain a benzodiazepine ring system? Then we can ask that question to the computer by framing it in a graph theory. We shift our thinking to the computer thinking, we frame it in a graph theory sense. We have something called the Ullman algorithm where we can give it a graph for the benzodiazepine or whatever, and then search through, nowadays, millions of compounds and find all the compounds that have a benzodiazepine in. So this graph theory, I'm actually using graph theory a lot in my research at the moment, both on the chemical structure, but also on networks of chemical and biological information. What's nice about this intersection of computer science and the science is we can pull out these kind of generic techniques and make them applicable to this specific domain. We can also do some other computer sciencey things. As I said, computers like ones and zeros. So if we can put things in a whole bunch of ones and zeros, we can do things with them on the computer. So one thing we do in cheminformatics is called a fingerprint. A fingerprint is meant to characterize the features that are present in a chemical structure. And we do that by breaking structures down into lots of substructures. And then we can have these dictionaries or sets of descriptors of a molecule which say whether or not these particular features exist in a particular molecule. So does it contain a benzene ring? Does it contain a imidazole? Does it contain a sulfonamide? And so on. So we can represent that yes or no situation for a lot of different features as ones and zeros. The computer loves the ones and zeros, and we can do things like calculating similarity between bit strings. So being able to then characterize the molecules as bit strings, we can then have a way to calculate similarity between molecules. Here's a kind of little trivial example. Here we have a molecule on the left here. We have maybe part of a fingerprint. Fingerprints could be thousands of bits long or a few hundred bits long, depending on the system we use. But here we've got this bit position here might represent the presence or absence of a carboxyl group. Well, this molecule's got a carboxyl group, so there's a 1. This one represents a sulfonamide. Well, this one doesn't have a sulfonamide, so it's a 0, okay? So we get this bit string, and then we can, actually I lost the thing there. Then we can calculate, I think actually a bit later on I go into similarity, we can calculate the similarity between them. So these methods, these subgraph isomorphism, these fingerprint methods, enable us to affect these really important kinds of searching in chemical databases. So if you go to one of the popular chemical databases like PubChem or ChemSpider that Tony will be demonstrating next week, you'll see these kinds of search. Is this structure in the database? Find me all the structures that contain this substructure. Find me all the structures that are similar to this one. And we can affect that with these methods that we've pulled out of the bag. Is this structure in the database? Is this substructure? Find me all the structure that contain the nitro group. This is a subgraph isomorphism problem. And so we can run the algorithm and find answers to that. Going back to the similarity, show me the structures that are highly similar to this substructure. How can we do that? Well, we generate fingerprints for, I'm going to zoom ahead a bit here. I guess I didn't put that slide in. We generate fingerprints for each of the compounds, and then we can calculate something called the Tanimoto coefficient, which is a measure of bit string similarity between the two bit strings and come out with a number between 0 and 1. So we can rank the whole of PubChem, 60 million compounds, and just pull out the ones that are highly similar to another compound. You can actually do this yourself. There's a little tool called MolInspiration. You can do some little searching. You can do it on ChemSpider. You can do it on PubChem. These are some hits. With that measure of similarity between compounds as well, we can do some higher level things like cluster analysis. Cluster analysis lets us say, well, let's not just find all these things similar to this one thing, but let's look at the similarity between everything and everything else and try and get them into groups. So we can group chemical structures into clusters of similar compounds and then do things with those similar sets. We can do something called diversity analysis, which is kind of the opposite of clustering. You say, how diverse is this data set? This came up because in the pharmaceutical industry, there were people offering to sell pharma companies, hey, we've got 200,000 fantastic compounds we can sell you for $10 million. It's like, well, you know, we've already got 1 million compounds. Are these 200,000 going to add anything, or are they just like the ones we've already got? Well, diversity analysis answered that question by putting a number on how diverse a set of chemical structures is, and how much more diverse it becomes by adding new ones in. And so we get these, people talked about these chemistry spaces. This is this was from a paper in the 90s when diversity analysis was big. Here was actually properties, looking at the properties. This was, at that time, Park Davis's corporate data set, and this was how that data set was distributed in this kind of chemistry space. And then they started to look, you know, we haven't got many compounds in here, so if we can find some compounds to fill the gaps here, then we might be able to find some better drugs into it. So we've been talking so far about 2D, but we also have 3D structures, 3D chemical structures. These are a little different, as in whereas a 2D structure can be kind of just intellectually derived from the knowledge of the atoms and how they're bonded together, a 3D information really has to be experimentally derived. Molecules exist in 3D, they're wiggling around all the time, moving around, and in fact that's even just a model. It's really a quantum mechanical fuzzy event of all this stuff going on. But notionally we can think of the atoms and bonds twisting and moving around. So we can take snapshots of that in various experimental ways, particularly X-ray crystallography and NMR spectroscopy can take a compound in a particular situation, in a crystal, in the case of X-ray crystallography, and then resolve the relative positions of the atoms in the molecule. So you can come out with this 3D structure. We can also create computer-generated 3D structures as well, which we'll get to in a sec. But this is all very complicated because, you know, we're dealing with a very dynamic situation in 3D, so and all kinds of complexities. There's a very nice data set called Cambridge Structural Database of experimentally derived chemical compounds from University of Cambridge derived. As for representing 3D structures on a computer, we really the basic thing we do is extend that atom lookup table to be a coordinate table that has the 3D data in. So we can just have relative 3D coordinates of atoms added on as well as the atom label. So that kind of solves our basic internal storage problem for 3D. We can also generate things like a distance matrix, which can be useful for some graph theory things, which tells us the distance in angstroms between every atom and every other atom. Again, it's a matrix, so the computer likes it. I also have other forms of 3D information. This was a topic of my PhD thesis. I looked at electrostatic, steric, and hydrophobic fields around molecules. We can have atom-based properties, hydrophobicities and things, properties projected onto surfaces, all kinds of things can come up in 3D. So some of the important things we do in 3D is simply visualizing. If you have a 3D structure, visualizing is important. It's a very nice little tool called JMOL, amongst others, which let us visualize 3D structures. Often what we want to do is visualize chemical compounds, as in this case, in the context of a protein target. We have all kinds of what we call molecular modeling packages that let us not just visualize 3D structures, but can also do things with them, make predictions and this kind of thing. One of the things we can do in 3D is called molecular docking. If we've got a 3D structure of a protein target, which can also come from NMR or X-ray techniques, and some information about where we think drugs are binding into that protein target, then we can actually make a computer prediction of how we think that compound is going to bind into the target. How do we do that? Well, we use optimization techniques. Again, we take something from computer science and then we kind of tailor it for cheminformatics. Here's an example of how we do that with genetic algorithms. A genetic algorithm is a purely computer science method that kind of borrows ideas from Darwinian evolution, where we start off with lots of potential solutions to a problem and use something called a fitness function together with kind of randomization methods to try and get to an optimal solution to a problem. In this case, the solution we're trying to get to a problem we're trying to get a solution to is wiggling the bond, rotating a molecule around in 3D and twisting the bonds. So I optimize the chance of things like hydrogen bonding going on between a a drug molecule, say in a protein target. This is actually a real example of a program called GOLD, which is a docking program, which makes a prediction of how this particular molecule is going to fit into a protein target. We're showing some of the residues of the protein target here. And docking is now very well established as a way of making predictions. It has variable results depending on the circumstances, but it's a very well established method. We can also use a variety of methods like docking. We can also use similarity-based methods and various other techniques for what we call virtual screening. Now, one of the big developments in experimental methods has been what's called high-throughput screening, where we can biologically test a molecule for biological function. We're doing on millions of chemical structures within the space of maybe a day or so, and we have these incredible plates with thousands of wells in with different compounds in each, and you can squirt in an enzyme and do an assay on all these compounds. But we can also do a virtual version on the computer. For instance, we can have a protein target, and rather than physically binding it, we can make predictions of binding. So very well established the idea of virtual screening, where we make predictions of whether or not we think a compound is going to bind into a target. We can do these kind of plots where we look at, we can do tests where we look at the amount of actives found versus ranking of those virtual screens. And this will be a random line up here. So sometimes with these methods, we get, this will be like an ideal situation where we pull back all the truly active molecules, and often we'll get something like this going on. So, there's some pretty good techniques out there now for virtual screening. For a while, in some cases, the virtual screens work better than the real screens because you get all kinds of error issues with real screens too. We can do a little bit of this online with some predictive models. One thing I haven't really mentioned as well is using machine learning. So we can use machine learning methods to actually make direct predictions as to whether we think compounds are going to have particular biological activities or not. So that was like the 200 miles an hour zoom through everything that's been learned in cheminformatics in the last 30 or 40 years, maybe 50 years. The last couple of slides, I just want to focus on some ideas about where cheminformatics, I think, is going in the next 20 years or so on. Cheminformatics traditionally heavily related to drug discovery, and that's taking on all kinds of new dimensions now with things like what's called chemogenomic effect of chemicals on all the genome as a whole, on your body as a whole, rather than just on a particular target, with understanding the complexities of how compounds relate to side effects and diseases and such like. Massive amount of interesting work to do there, and that's really where my research focuses a lot, and that links to biology as well. Action of small molecules in cell, chemical probes of protein function. We can use what chemicals bind to proteins as a way of understanding what their functions are. Something called systems chemical biology is gaining ground, which is really having bringing together cheminformatics, chemistry and biology and systems biology all together to get a kind of complex understanding of what's going on in the body. A lot going on the web, particularly with information mining, aggregating information, pulling information from multiple sources. Tony's done an amazing job with ChemSpider at integrating lots of information that's available on the web and elsewhere. Also, one under-researched area, I think, is green chemistry. We now do things like predicting toxicity. A lot of kind of emphasis on that is the EU REACH thing. The EPA is really emphasizing computational toxicology, things like safer and better pesticides, biofuels research. Very little being done on this so far, but I think is a big opportunity. I was asked a few years ago to be one of the editors of a new journal called the Journal of Cheminformatics, just jcheminf.com. But I talk about what I think are some of these emerging areas in the opening editorial of that journal. So if you're interested, it's just at this website, jcheminf.com, content 111, or you can search for it on the web. It's called Grand Challenges for Cheminformatics. And finally, no professor's talk can finish without a plug for his or her own research. So If you're interested in what somebody like me who's involved in cheminformatics is doing nowadays, if you go to djwild.info, there's various presentations I've given recently and tools and papers that we've written and that kind of thing. And I think I'll stop there to give us a little bit of time for any questions that there are.
Okay, well, thank you, Tony. Okay, can you hear me?
Yeah, I can hear you just fine.
Okay, great. Do we have any questions? What I'd like to do is hand out the microphone, and I think we have another microphone that we can bring down here. And please introduce yourself and hold the microphone about 3 to 6 inches from you.
My name is Tito Viswanathan. I'm a professor of chemistry here at UALR. My question is, how do you convert three-dimensional data into the linear format? Just like the smiles you said, that seemed easy, but how do you convert three-dimensional data into that? And there are so many different conformations that the 3D can have. So do you have a linear thing for each and every?
Yeah, right, good question. I kind of skipped over that one, but we don't really have a good linear representation for 3D. It has been done just by tagging on coordinates to atoms. There's something called Symbol Line Notation, SLN, that did that. But really what we usually end up doing is having a more verbose format, file format, which I didn't really go into, that really just does a dump of the coordinate table and the connection table into a file for that. You mentioned conformations. That's something I just briefly touched on, but that's a really big problem. Conformational flexibility is a big problem. We can handle it. There's two ways it's handled in cheminformatics. One is to produce lots of conformers for a particular molecule. So you say, let's find the 100 most likely low energy conformers for a compound and just generate them. And then in any algorithms we use, we just treat them as rigid, but we treat each one separately. Or we can have algorithms which act like the genetic algorithm, which actually try and flex the bonds and such like. This brings up kind of the fact that in some ways, people always expected 3D to be fantastically better than 2D in terms of things like, how well it predicted biological activities. And that didn't really pan out. 3D is really useful, but one thing we've kind of found is that representing 3D information badly is often worse than representing 2D information well. So we really have to be careful with 3D, and there's been a lot of research done on this as to when to use it and what to use it for, and how to handle things like conformational flexibility. Still not fully resolved because it's such a difficult problem. We can create a lowest energy conformer in vacuum, but that can bear no relation to what's happening when it's sloshing around in a complex. It goes through your stomach and pH and complex solvent, going into a protein target in your body, and all kinds of dynamics going on. So 3D is really complicated. We're still treating it fairly naively.
So where do you think the future is taking us? What do you predict in the future? How good is it going to be?
I think we've kind of plateaued. Others would disagree with me. One thing I often say about cheminformatics is I think there's some problems like 2D representation, basic representation, we've solved really well. It's now kind of commoditized. Things like 2D similarity, people are not really doing that much research anymore. It's not perfect, but we've kind of done it. We've established our way of doing it. And these other problems like green chemistry and systems, chemical biology, which are very new and we're just learning about. But there's this stuff in between which has been around since the start. And we've kind of, there's huge effort put into them into the 80s and 90s, like getting 3D methods to work better. But we've really hit diminishing returns. We've got docking algorithms now which are quite good, but we haven't had recent massive breakthroughs in docking algorithms which make them work so much better. So there's been a kind of plateau over the last decade or so of improvement in those basic kind of complex but basic methods. I'm interested in the third category of problems for my research. I'm interested in the really new directions. So I'm kind of, I'm really glad other people are researching and trying to improve those methods, but I kind of get less interested in that because I don't hold out too much hope for being able to make big breakthroughs in that area.
Any other questions? Okay, well, I might like to ask a quick question. My interests are more with the on the web level stuff, and I sort of have two questions. The first one is you mentioned the linear strings with smiles and Inchi, and I know that we've had to use Inchi keys and stuff. Could you describe very quickly a little bit about the advantages or disadvantages of Inchis and why we need Inchi keys?
Yeah, sure. I really thought I'd put a couple of slides in here about Inchis, and I realised I somehow didn't. But yeah, Inchis. So Inchi is actually something which is supported and blessed by IUPAC, the International Union of Pure and Applied Chemistry. So it has a lot of weight behind it, and it's really very, in some ways, it's similar to SMILES, but it's more organised in a way that represents. It has different sections in an Inchi that represents more subtle things. So the first section just represents what the atoms are, how they're bonded. Then moves on to things like tautomerism and which different tautomers are valid and various complexities. So you can actually chop bits off an Inchi. You can just use the first bit, which is the basic stuff, or add in the more subtle stuff. So it's pretty powerful in that regard. And Inchi key also reflects that. So Inchi key is specifically developed for web searching. The problem with doing a Google search for SMILES or Inchi even is that they have lots of symbols in them. So Google tends to split them apart, and then you just get bits of things, and you can get a real mishmash of kind of pages that have nothing to do with chemistry. So the idea of the Inchi key was to come up with a kind of unique, almost unique identifier for a compound, which was unusual enough that if you do a Google search for it, you're not going to hit some web page about something nothing to do with chemistry, but you would really hit on it. And also it has two sections, again, one which is kind of general stuff, and then others which gets into more specific. So you can just use the general piece or the more specific one. And it does work with Google searching. So you can then search for an Inchi, it pulls them back. The problem right now is that Inchi isn't used universally. I've seen a really big difference since like a year ago and now in terms of what you get when you search for an Inchi key. So if you want to play around with it, if you go to like ChemSpider or PubChem, and I think hopefully Tony will demonstrate this a bit next week, you'll be able to get the Inchi key there, and they can just take that and search in Google and see what you come up with. But it's kind of developing thing. The Inchi key is also loses the human ability to decipher it. So it no longer contains in itself information. It becomes purely an identifier, whereas the Inchi has that information in it itself. Did that answer your question?
Yes, it did. And we still have a couple minutes. We have a few more questions. Good. Michael, Andrew, why don't you give it to Jeff, and I'll get up first.
Enjoy your seminar. It's Jeff Gaffney.
Could you introduce yourself, please?
Yeah, I'm Jeff Gaffney. I'm chair of the chemistry department here. And my best to Ron Heitz and I believe Kate Rex working at your school these days.
Yeah, right.
Yeah, tell her I said hello. She'll say,
yeah,
oh my God, Jeff Gaffney.
Yeah.
She and I go back a long way. I just came back from NIH. And now we've got a new faculty member, Darren Jones, who's come from Pfizer, and so I really can see all the linkages and the ideas of docking these things together, et cetera. But one of the areas that I brought up with them that I think is going to be an area of the future that we really need to address is, and this comes to the fact that I've been working in environment for a long, long time, and that is if you can't lick them, join them. So I'm now joining the nano science and technology area. And so one of the things I asked them is about these new nanomaterials. They're trying to get what they're calling now Theradiagnostics or Theranostics. I don't know if you've seen this. It was on CNE September 26th issue. And I talked to the gentleman that was highlighted in some of that work. But what they're trying to do is now is to get fairly large systems. They're almost looking to me like we're essentially generating protein-like structures and mixing them now with the proteins. Mm-hmm. I can see that as you start to get into this more, that unless you really understand what the shape and the chemistry of nanoparticles are going to be doing, it's going to be hard to understand what their toxicities are.
Yeah, right. Sorry.
That's okay. I wanted to make sure you were still there. Do we have the computing power to do this kind of stuff these days? I mean, I would assume that if we, use Oak Ridge supercomputers and things that we can start looking at 1,000 angstrom?
Yeah.
You know, I mean, we're talking huge differences in lengths from what you guys have been doing.
So with 3D methods, most 3D stuff that's been done historically in pharma and such like has been kind of static, as in we're not talking like molecular dynamics or quantum chemistry or anything. We're talking, at most we're talking kind of Newtonian model where we're trying to wiggle this thing around and put it into an active site. So all that stuff is actually, we can do, we can screen 60 million compounds or 60 million protein targets, if you like, within a matter of hours.
Right.
So as long as we're sticking with that crude level, then computational expense isn't a big issue. On the other side, we've got all these techniques which historically just haven't been used which have only been used when you're dealing with one compound. Quantum chemistry and molecular dynamics. It's interesting that in academia we use those techniques a lot, because often in academic chemistry departments we're dealing with a reaction or a compound. In pharma they're dealing with thousands of the things. So they just throw up their hands and say we can't do this stuff. That's now changing a bit as computation, particularly with cloud computing. You can just buy time on Amazon. You can actually start to do those kind of calculations on bigger systems and many more systems. So there's kind of interesting overlap area between the two. So I think I've actually talked with a few people in chemistry here at IU about that, and in fact, there's somebody here who was working on the whole kind of nanochemistry area, but there's very little been done. It's like the green chemistry. I think there's very little been done, and we're going to have to explore it as a new area. Cheminformatics has been used in materials chemistry quite a bit with polymers, but that may or may not be able to be mapped onto this area.
Thank you.
Okay, I'm Matthias Prochhausen from the Division of Biomedical Informatics at University of Arkansas of Medical Sciences, and I have a small question. So I was a bit surprised when you said that it might be useful sometimes to use canonical smiles, because for us in biomedical informatics, getting the same stuff, the same code for the same structure is a vital issue. So how does it work? If you don't use this canonical smiles, will you? Is there any automatic way to reconcile different smiles you derive from same structures? And as a small afterthought, you mentioned AI techniques, and I would just be interested whether ontologies are one of the AI techniques you used, and if so, what your experiences with those are. Thank you.
Sure. Yeah, firstly on the smiles, I mean, the bottom line is you should never use smiles as an identifier for databases and searching, even if you use canonical smiles, because the problem is that you can then have different canonicalization algorithms. So if you want to do the search, is this structure in the database, you instead do a graph isomorphism search, which doesn't require a canonical smile. So in some instances, in a database, you don't actually really need canonical smiles, because even the canonical smiles isn't correct enough to be able to allow indexing and searching and such like. So usually, for instance, in PubChem, we have a CID, a compound ID, which uniquely identifies a compound. And also, two different compounds can have the same smiles if they have subtle differences. Or there might be two different mixtures or two salts or something. So we need to be able to have the same smiles for multiple instances in the database. So we just throw up our hands and say we're not going to use smiles as an identifier. So in that case, it doesn't necessarily really matter whether it's canonicalized or not. For the second question, yes. But actually, my research area is looking at applying semantic web methods in kind of integration of public chemical and biological data. So we've actually we have something called Chem2Bio to RDF, which is a big RDF integration, and we've created an ontology for that. So ontologies are becoming really important. We've always had this problem of, do you have this grand ontology that you get all the experts to agree on, or does everybody just make up their own ontologies and then try and link them together? And we're still kind of working that one through. I think it's kind of moving towards the latter now. And then we have these things like BioPortal and such like, where we try and kind of reconcile them. But yeah, for that, having an ontology has been very useful because we can make equivalences between data sets without having to have them explicitly laid out in the query. So there are some chemistry ontologies, there's some ontologies of even like chemical fragments and compounds. We've done one for compounds to genes, and then we're trying to integrate that with some of the biological ones like Bio to RDF and such like.
Question?
Hello, my name is Darren Jones. I'm the new guy in the chemistry department here at University of Arkansas in Little Rock. I have two questions. One's kind of quick, and I think it's probably obvious to you. The first one is, whenever there's something interesting to the pharmaceutical industry from a therapeutic perspective, the patents out there, they all tend to look very similar from the pharmacophore itself. I'd like to know if people use this type of tool as a way to identify potentially new pharmacophores. For example, like an indole to an indazole to an indoline, so on and so forth. Then the second question I have is, this high throughput screening or fragment-based screening, all these kind of things, they tend to look at just whether it's a good binder or not. You get your score out and you say, these are good binders, these aren't. But when are they going to start to incorporate a lot of the drug-like properties from, like Lipinski type rules, things like this?
So the first question is, I'm sorry, let me just, actually just remind me what the first question was. Sorry, I got thinking about the second.
Yeah, it's okay. So, people patent essentially the same Marquis type pharmacophores.
Yeah. So this has been very central by going a long way back. I remember on my PhD, I did an internship where my job was to try and have a searching system that could beat the competitors' patents. But it's kind of called scaffold hopping is the way it's called. So, there's a bunch of compounds which are active, which have a particular chemical scaffold. Can we find different scaffolds that would arrange the functional groups in a way that would achieve the same ends? There's been all kinds of different approaches to that. That's one area where 3D is really useful, because the 3D pharmacophore, you can specify exactly where you need to bind to the protein, and then you can you can try and fit molecules into that. So that's a definite use, particularly of 3D, but there have been a whole variety of approaches for scaffold hopping that have been examined. There's also been a bunch of techniques for encoding and trying to decipher patents, but it's a horrible problem because patents are written by lawyers to be deliberately vague, and the vagaries get battled out in court. So trying to work that through the computer gets rather difficult. The second question is, for drug likeness, there's that can come in at different points. So there's been traditionally, you either apply drug likeness of a molecule at a very early stage. So we're not even going to look at compounds that don't follow the Lipinski rule of 5. You exclude them, and then you just screen compounds which pass and put them through docking or whatever. And then the other end is say, we're going to let everything in, but once we get some interesting compounds, we'll then start to filter them. It tends not to be integrated into the docking algorithms as a whole, for instance, because it's a property of the whole molecule. So it doesn't vary according to how the molecule moves around in the active site. So it tends to be handled separately. But there's always this problem that Pfizer's blockbuster drug Lipitor crashes through at least 2 of the rules of 5. So you get these exceptions to the rule. In some ways, a few of his people said, hang on a minute, should we be looking for the exceptions, because they might be the really unique molecules that nobody's thought about before. So again, I think people often do filtering on rule of 5. There's also been some work by Tudor Opria and others on lead likeness rather than drug likeness. So is this compound likely to be one which would in vitro be active, but not, without worrying about in vivo? Chemists always say, we can always modify it to be work in vivo and blah blah blah. So it's not always clear where to apply those kind of things. I guess that was a long-winded answer to that. But
Dave, before we say goodbye, I wanted to ask Tony, are you still lurking? Okay, I guess Tony's not lurking. Okay, good. I just wanted to be sure. Tony of the Royal Society.
I'm here.
You're here. Did you have any questions or comments you would like to ask or make?
Yeah, next week I will make sure that I cover some of the details around INSHE. I will certainly be able to show why the SMILES issue and canonicalization is causing us problems with integrating data sources together on the web. SMILES has been incredibly useful, still has an incredible amount of value, but for some of the searches that David was talking about, how to link resources together on the web and do searches via standard search engines, INSHE has really taken over there. And I'll be able to focus a lot of effort into that area. And she's become a very enabling technology for internet-based work. It's used now by many publishers. It's on most electronic databases with chemicals in. So I'll definitely talk about that.
Okay, and you have no questions for Dave?
Yeah, I've sent him one. Send me a copy of his slides, because I'll use them as a catalyst for some of the things to discuss next week.
Okay, well, Dave, thank you ever so much for your time and for contributing to our seminar.
Great. Well, thank you, and thank you all for coming. That was fun for me. I hope it was for you too.
Thank you.